2019, one of the brightest stars in the night sky began to fade, not slowly, not subtly, but enough that astronomers around the world stopped what they were doing and stared at their data in disbelief. This wasn't just any star. This was Betelgeuse, the red supergiant that marks the shoulder of Orion, a star so enormous that if it replaced our Sun, it would swallow Mercury, Venus, Earth, Mars, and stretch nearly to Jupiter, a star that humans have watched, named, and mythologized for thousands of years. A star that, quite suddenly, was growing dim. Within weeks, headlines exploded. Was Betelgeuse about to go supernova? Were we about to witness a stellar explosion bright enough to rival the full moon? Social media buzzed, news outlets speculated, even professional astronomers admitted something was off. Because stars don't just do this. Yes, Betelgeuse has always been variable. It brightens and dims over time, that part was known. But this was different. The dimming was deeper, faster, stranger. By early 2020, Betelgeuse had lost a significant portion of its visible brightness, becoming noticeably fainter to the naked eye. For the first time in recorded history, one of the most familiar stars in the sky looked wrong, and that raised an unsettling question. Was this the beginning of the end? For a brief moment, it felt like the universe was giving humanity a front-row seat to something cosmic and catastrophic. A nearby star nearing the end of its life, possibly collapsing in real time. Telescopes across the world turned toward Orion. Space observatories joined in, data poured in, and yet the more scientists looked, the more confusing the picture became, because the numbers didn't quite add up. The dimming didn't match a dying star's final heartbeat. The energy signatures were strange. The behavior didn't fit the models. Betelgeuse wasn't exploding, but it also wasn't behaving normally. For years, astronomers had noticed odd patterns in its light, its surface, its atmosphere, clues that something complex was happening beneath the glow. The great dimming wasn't the cause of the mystery. It was the alarm bell that forced everyone to pay attention. And now, after decades of observation, advanced instruments, and patient analysis, scientists believe they may finally have the missing piece of the puzzle. Because Betelgeuse isn't just changing from within, it may not be alone, and the real explanation for its strange behavior is far stranger than anyone expected. A star like no other, Betelgeuse is not just another star in the sky, it is a red supergiant, a rare and extreme type of star that represents one of the final phases of stellar evolution for massive stars. Located about 640 light-years away in the constellation Orion, Betelgeuse marks the hunter's shoulder and is one of the easiest stars to recognize with the naked eye. Its reddish hue is a direct result of its relatively cool surface temperature compared to stars like our Sun, and that color alone signals that this star is already living on borrowed cosmic time. To understand why Betelgeuse commands so much attention, you have to understand its size. Betelgeuse is so large that if it were placed at the center of our solar system, its outer surface would extend beyond the orbit of Mars and possibly as far as Jupiter, depending on how expanded it is at a given time. The Sun would look like a grain of sand by comparison. This immense scale is not just impressive, it fundamentally changes how the star behaves, how stable it is, and how it interacts with its surroundings. Despite its size, Betelgeuse is surprisingly light for how big it is. The star is only estimated to be around 15 to 20 times the mass of the Sun, spread out over an enormous volume. That makes it more like a glowing cosmic balloon than a dense object. Its gravity at the surface is extremely weak, allowing gas to rise, fall, and even escape into space far more easily than it could on smaller stars. This loose structure plays a major role in its dramatic and sometimes chaotic behavior. Betelgeuse is also old, at least by stellar standards. It has already burned through the hydrogen fuel that powers stars like our Sun and has moved on to fusing heavier elements deep in its core. The patterns in the star's variability, previously attributed only to internal processes, suddenly made much more sense. The discovery of Siwaha also highlighted the ingenuity of modern astronomy. Detecting a faint, invisible object in the presence of a supergiant star requires extraordinary precision. Scientists had to combine ultraviolet and infrared imaging, spectroscopy, and years of observational data to trace the wake and confirm the companion's orbit. It was a process akin to inferring the presence of a ghost by watching how it moves the air around it, subtle, indirect, but undeniably real. This revelation fundamentally changes how we understand Betelgeuse. The star is not an isolated giant, pulsating and shedding material on its own. Its irregularities are influenced by the gravitational pull and motion of a nearby companion, adding a whole new dimension to the star's life story. Siwaha's wake, the turbulence it creates, and its repeated interactions with Betelgeuse's atmosphere explain many of the long-standing mysteries that had frustrated astronomers for decades, and this changes how we understand Betelgeuse entirely. How the companion changes Betelgeuse's behavior. The discovery of Siwaha provided astronomers with a key to understanding Betelgeuse's long-standing mysteries, and the effects of this hidden companion are both subtle and profound. As Siwaha orbits through the outer layers of Betelgeuse's atmosphere, its gravitational pull stirs the surrounding gas, creating turbulence and waves that ripple across the star's surface. These gravitational interactions are not violent enough to damage the star, but they are strong enough to reshape the flow of material, pushing gas into denser regions and influencing how light escapes from the star. This stirring has a direct impact on the star's outer layers. As Siwaha moves through the atmosphere, it compresses pockets of gas, raising their density and triggering local cooling. In these denser, cooler regions, atoms begin to bond and form dust grains, similar to how condensation forms on a cold surface. The dust clouds generated by these interactions can block visible light from Betelgeuse, causing sudden drops in brightness that appear as irregular dimming events when observed from Earth. Over time, these interactions can amplify Betelgeuse's natural variability. The star already pulsates and has massive convective cells, but Siwaha's repeated passages through the outer layers create additional layers of complexity. Bright hotspots shift, gas flows unpredictably, and dust clouds form and dissipate on irregular schedules. The result is a star that appears erratic and unpredictable, with cycles of dimming and brightening that do not follow a simple pattern. What once seemed like random behavior now has a plausible cause: the presence and motion of a companion star. Astronomers have also used computer simulations to model the effect of a companion moving through a red supergiant's atmosphere, confirming that gravitational stirring and gas compression can account for many of the irregular brightness fluctuations observed in Betelgeuse over the past decades. These models show how a hidden companion can interact with the star's convective cells, create temporary dust clouds, and subtly shift the star's luminosity over time. The patterns observed now fit with predictions, giving scientists confidence that the mystery of Betelgeuse's strange behavior is finally being unraveled. But while these findings explain the unusual light curves and irregular cycles, they also raise the obvious question: if Betelgeuse is being stirred and compressed by a companion star, does this mean it is on the verge of exploding? Is Betelgeuse about to explode? Despite all the drama of the Great Dimming and the discovery of a hidden companion, Betelgeuse is not on the verge of exploding tomorrow. To understand why, it helps to know what triggers a supernova. Stars like Betelgeuse end their lives when the nuclear fuel in their cores runs out. Once the core can no longer produce the energy needed to counteract gravity, it collapses, triggering a catastrophic explosion that blows the star apart. This process requires specific conditions in the core, including the buildup of iron and an inability to sustain fusion. Although Betelgeuse is in the late stages of its life, its core has not yet reached the critical point for collapse. Astronomers estimate that the star still has tens of thousands of years before it goes supernova. In the context of human history, that's an almost incomprehensibly long time, but in the life of a massive star, it's the final chapter of a long and dramatic story. The sudden dimming we observed and the effects of its companion are dramatic, but they are surface phenomena. They do not indicate that the core is about to fail. Our perception of urgency is distorted by human lifetimes. A star can behave unpredictably, eject massive amounts of gas, or dim dramatically over a few months or years, and yet these are minor events in the context of cosmic time. What seems sudden and alarming to us is, for Betelgeuse, just another fluctuation in a life that spans millions of years. This perspective helps astronomers remain calm while still studying the star closely to understand its behavior. So while the idea of a nearby supernova naturally stirs our imagination, the reality is reassuring. Betelgeuse will continue to captivate observers with its pulsations, dust clouds, and interactions with Siwaha for many generations to come. And yet, the knowledge that one day this massive star will explode reminds us of the raw power of the universe. When that day finally comes, it will light up the sky in a way humans have never seen before. But when it does happen, it will be unforgettable. Why this discovery matters. The discovery of Betelgeuse's hidden companion does more than solve a decades-old mystery. It reshapes our understanding of how massive stars live and evolve. Until now, many models of the Great Dimming that shocked Earth By the end of 2019, something unprecedented was happening in the constellation Orion. Betelgeuse, normally one of the brightest stars in the winter sky, began to dim dramatically. Astronomers measuring its brightness noticed a sharp decline starting in October, accelerating into November and December. By early 2020, the star had faded to roughly 1/3 of its usual brightness in visible light, an event so extreme that it stood out clearly in long-term observational records. Nothing like this had ever been documented for Betelgeuse before. This change was not limited to professional observatories. Amateur astronomers and casual stargazers around the world could see it with their own eyes. Orion's familiar shape looked subtly wrong, with Betelgeuse no longer dominating the constellation the way it always had. Reports flooded astronomy forums as people compared photographs taken just months apart, clearly showing the star's dramatic loss of brightness. For a star visible to the naked eye to change so much in such a short time was deeply unsettling. As the dimming deepened, speculation exploded beyond the scientific community. News outlets began asking whether Betelgeuse was about to go supernova, an event that would create one of the brightest objects ever seen in Earth's sky. From Earth's point of view, this newly formed dust cloud partially blocked Betelgeuse's visible light, making the star appear much dimmer, even though its internal energy output had not dramatically changed. This explanation began to solidify as data poured in from multiple observatories. The Hubble Space Telescope detected changes in Betelgeuse's outer atmosphere, revealing regions where material had been lifted away from the star. At the same time, ground-based telescopes tracked the star's fading and recovery over many months, confirming that the dimming was uneven and directional rather than uniform. This matched the idea of a localized dust cloud drifting across our line of sight rather than a global collapse of the star itself.